What we're going to talk about today is some best practices when it comes to milling. Okay, even though I'm a milling guy, for many years we have been considered somewhat of a black eye because maybe the quality of work that we do. Okay, so times have changed somewhat. So if you ask what is milling, cold planing, profiling, ARA is the Asphalt Recycling Reclamation Association. Okay, we have this big long paragraph as far as describing what milling or cold planing is. I kind of think of it from an artistic standpoint. Our jobs as milling operators is to give that paving crew a clean palette to pave a masterpiece on. That's our job. It all starts with us. So basically, if you strip the machine away, this is what you're looking at, the cutter drum assembly. It's an upcut situation majority of the time. You can see the way the drum is wrapped, it's kind of designed to auger material towards the center to be ejected out onto a conveyor. So basically, that's the drum without anything around it. Before we start milling though, there's some questions that we need to ask. Do I have the right setup of my machine to achieve quality results? This is kind of a loaded question. To the best of my knowledge, do I know the material I'll be milling or profiling? Does my crew have an understanding what needs to be done? And can I profile or mill for quality and achieve my quantities? So basically when it comes to equipment, what are we looking at? Can we get away with just running a small size machine? Say if we're just doing some curb reveal, zipping around some manholes, stuff of that nature. Are we on city streets where we're actually going to have to bring in a bigger, say, half-lane machine? Or are we breaking out the big kid, putting it on the interstate, full lane width head? This is the things that we need to understand, because we don't want to show up on this interstate job knowing we need a full lane machine, and we show up with a small machine. It's going to be a long day for us. So to the best of my knowledge, do I understand the material? Okay, I say this is a loaded question because we all have roads that look like this. We want to make them look like this. When it comes to milling though, we only can really see what's on the surface. Okay, and we get into residential city areas, we're not sure what's really underneath that asphalt. You may run into some buried railroad tracks, manhole covers, trolley beams, random steel. Okay, milling machines of any manufacturer do not like eating steel. Okay, it's not on its top to-do list. So if we understand there is steel there, we need to take precautionary steps to make sure we either remove the steel, mark the area out to where the machine does not take a chance on damaging itself, and it's also, let's just face it, it is a safety issue as well. So does my crew understand what needs to be done? Everything can sound real good in the office, but it's how we relay this information to our people in the field that counts. Okay? I personally have had a situation some years back. They said, yep, you're going to be milling I-55. Start here, take off. I'm like, that's great. We sit down, we start cutting. State personnel comes speeding up. I said, what are you doing? I'm like, we're cutting what you told us to cut. They said, no, we want an I-55 northbound, not I-55 southbound. Never a good day when you have that situation happen. It all boiled down to we didn't have the information needed. Okay? It allows the crew in the field to say, okay, we have 100% information, we understand what needs to be done, now we come up with a plan ourselves as far as how do we accomplish this goal. Okay? It's all about communication. Communication is everything. So I need to understand what kind of automatics or controls I need on my machine to achieve the quality that I need. With today's machines, running a grade control system, there's a variety of different sensors from smart cylinder technology, wire ropes, sonics, and the latest craze right now is 3D. Okay? But we need to understand the application, which is going to be best suited for us to achieve that quality. Okay? Because if we go out there and we don't have the necessary tools, it's going to make it very difficult for us to give that paving crew the quality product they need to also achieve quality product. So with new machine controls, I mean, it's kind of like work smarter, not harder. Okay, with all the new machines from all the manufacturers, there are tools there to help you achieve the quality without having to work as hard. Okay, these are tools, if the machine has it, I strongly suggest utilize these tools because it's only going to make life a little bit easier. If you don't mind, multiplex or sonic averaging systems. Okay, with sonic averaging systems, there are a lot of companies that have sonic averaging systems but don't run them. This is not only for milling but also with paving. If you look at a normal milling machine, what happens is it's usually referencing off the side plate. So now it's a small area. With a sonic averaging system, now you're referencing over the length of this machine. So now it's going to take out those deviations much more. It's going to be a much more fine scenario. So if we have a rippled road, it's going to allow you to take out those ripples instead of running off this side plate, which what's that side plate going to do? It's going to ride right there with it. So you're really not taking out the deviations. We're really not correcting the problem. We're just making it deeper. Okay, makes sense? So we start off, we need to zero out the machine. Okay, when I say zero out, the 0 point is point of contact in which the drum makes with the surface. Now, it's not always going to be the easiest thing to do because obviously if we're coming out to mill, the road is pretty much messed up anyway, but we try to find as level of an area as we can. We want those teeth just scraping the entire width of that drum to establish a quality 0 point. So when we've established this 0 point, and here is one of the biggest problems we have when it comes to milling. So we start off, we engage the automatics, machine's going to put itself into the cut. The first thing everybody wants to do, go. Because we've got that production mentality in our heads, we gotta go, we gotta go. But what happens is a lot of times, instead of going slow, they will go fast. When those rear tracks walk into the cut, if we're going too fast, the hydraulics of the machine do not have time to react. So now instead of cutting, say 2 inches, we're going to have a dip. It's a small area, but we've just changed some asphalt quantities. We've also changed the way that paver is going to have to start off now. Because if you think about nulling out a screed, when it comes off that joint, if there's a dip right there, what's going to happen? Screed's going to want to dive. That bump, we started it, it's going to be with us when we pave it. So when we start off, we need to understand how to line up. So machine's moving this way, drum's turning from this picture clockwise, it's an upcut. You always start on the rear. Now depending on which manufacturer, there's usually either in centimeters or in inches, it tells you what it is. Like on this right here, 4 centimeters, that's 1.54 inch. So once again, say we're trying to cut 2 inches, I'm going to start right behind that back bolt because the drum's turning this way and that's the point of contact for the teeth into the cut. I stop off the front just because that's point of exit of the tooth. Now the big problem we see is we'll make the initial pass with the machine. But when the problem is when we back up to make a second pass and we don't line up properly, we've got this area now to contend with. So now, we're utilizing more time to clean this area up to make sure we do have a straight joint to pave off of. Okay? And it could have been handled just by simply lining the machine up properly. Here's where a lot of people who've been around milling, it gets a little dicey here. Feet per minute versus your pattern. Like I said, we know we're in production mode. Go, 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 go. Get the machine down the road so we can get paving. Okay, this is at 255 feet per minute. This is not what you want to do because you can see the pattern behind there. Okay, machine can't keep up. This is in a residential area. That's at 200 feet per minute. We had 3 trucks. there's no reason to be going 200 feet a minute with 3 trucks. Here's the trade-offs of milling at high speeds. You're not actually cutting the depth you set. So once again, let's just use 2 inches as our baseline. What happens is, we've set it 2 inches, but when we're going that fast, remember, we're out there to cut for a reason. We're taking out deviations. But we're going so fast, we're not giving the machine time enough to react. So instead of milling 2 inches, we may be milling 1.5 inches, maybe going deeper, whatever. The machine's just not, it doesn't have the time to react. A poor pattern. What a poor pattern means is we have lessened the ability for interlocking a material of the pavement that we're going to pave on top of it. Think about Velcro. Velcro, you got to have both sides. So if you have one part of Velcro, the other side slick, she doesn't really want to stick that well. Now due to the erratic depth, now my asphalt tonnage is off. So not only have I affected the quality of my milling, but now I'm starting to affect the asphalt plant. Because if the job called for 5,000 tons, and my depth is constantly just irregular as it can be, am I actually going to be laying 5,000 tons? No. I'm actually going to have an overrun of material. My compaction numbers are going to fluctuate. Okay? So if my pattern, my peaks and valleys, that pattern are off, I got high spots and low spots, that roller comes over to compact it, it's just going to be hitting less, say hot asphalt, more of my high messed up milling pattern. I put an unneeded amount of wear on the machine. It's just these machines are designed to beat themselves to death. We don't need to help them along that way by going too fast. Sizing of material. You think about a lot of wrap material and these mountains of wrap material that we start to utilize with warm mix technologies and utilize them in hot mix technology as well. Now we've added the crushing screening process, where if you slow your milling speed down, you can size material to some degree. But when you're going that fast, you're just blowing up chunks. Okay? You're making it, you've added a process, and now we've added crushing and screening to the process. So all this equals is a low quality, wasted material, and loss of money. Nobody wants to hear loss of money. It's not what we do this. We try to make money, not lose it. So can I profile or mill for quality and achieve my quantity? If you look at one basic hour of operation, yes, there are the special circumstances where we've shut the entire road down, we've got more trucks than we can see, they're staggered just right, everybody's paying attention, everybody's on the same page. Those jobs are far and few between. So your standard milling job, if you look at it, in operation, you're actually only milling half the time in 1 hour. So say 30, 35 minutes. Between truck exchange, watering the machine, checking teeth, you're about a half an hour. So think about it. Instead of running at 130 feet a minute, imagine what's going to happen with your quality if you back it down to, say, 90 feet a minute. We're still achieving those quantities. But we are now obtaining a higher quality of material. So when you look at the milling drum again, and the line spacing, we call this line spacing because per revolution, one tooth makes one contact in that one line spacing. Okay? And we'll talk about some other drum technology a little bit. But that's what happens. So the slower my forward momentum of the machine is, the smaller bites per revolution that tooth is taking. Thus, the tighter pattern I'm achieving. So when I speed up to say 200 something feet a minute, that drum's only turning at a certain RPM. That's why you start to see that chevron or that skip, because it's not hitting uniform the way we need to. Or have you ever been on a milled surface where it's really rough, really coarse? It's because they've gone too fast and they're basically just dragging that tooth behind them, the machine, and it's causing us to have a more coarse pattern. So if you look at feet per minute, the one on the left, excuse me, on the right, it's 30 feet a minute. That's a pretty tight pattern. You can see at 60 feet a minute, I talked about how the drum kind of augured material towards the center. You can kind of see that V pattern, how that works. That's still a good pattern there. We start getting up to 85 feet a minute. That's where we start seeing that coarse, rough, milled pattern. You can see how it's starting to stretch out. You get up around 130 feet a minute, we call that chevroning. You're outrunning your pattern. Okay, that is low quality. So normal speed, let's say we're 80 feet a minute. That's a good pattern. I don't know of a state that wouldn't like that. That's some good uniformity. Nice texture for us to pave quality material. Now, we have to think about, when we talk about prepping our machine, some certain components that we need to maintain. Okay? These are high maintenance machines because, like I said, it's an abusive game. As far as components, from like our cutter drum, cutter housing, we need to check bearings on that drum, because if I say the bearing on the drum itself is loose, is that drum actually going to stay in line? No. The drum's going to want to move. It's going to affect our pattern. It's going to affect our quality. And it's also affecting the lifespan of that machine. The rear door, we call it the rear moldboard on the cutter housing itself. I think every manufacturer, it's adjustable down pressure. Okay? My rule of thumb is I run 0 down pressure. These doors are heavy enough by themselves. So if you have someone that's like, hey, I want that to be a cleaner cut, you know what? Maybe just turn the water up a little bit, because you can actually put enough down pressure on one of these doors. A, stop the machine. B, bend it. C, once again, we'll go with that benchmark 2 inches. Put enough down pressure, instead of cutting 2 inches, now I'm cutting 2¼ inches, say 2½ inches. Not only that, but I'm actually starting to take that pattern away. I'm removing that one side of the Velcro that I need to pave quality on. So I'm taking that interlocking capability away. Milling drum and the holder varieties, I mean, there's a plethora of milling drum technology out there, but this is a high maintenance thing. Just like when we talk about paving, you know, we have to maintain, say, the screed plates, augers. These are things we have to maintain in the paving train. We also have to do this on the milling side. So obviously the milling drum is taking the brunt of the abuse. It's the one in constant contact with the ground. Your typical milling drum, the way it's established, is you got 5 degrees of skew, like 36 degrees of angle, just so the action as far as how it penetrates into the asphalt. So we talk about bit rotation. Does anybody know that a milling tooth actually spins? They're designed to rotate. Okay? There's different technology out there. We're going to kind of concentrate on carbide milling teeth right now. And the way it's designed is once the drum makes contact with the asphalt, that tooth penetrates, it actually rotates once it releases from the cut. It may be a millimeter, maybe a couple millimeters. But then you have the other material from the next tooth over actually assisting the rotation of that tool. So that way we can get uniform wear of this tool. Now when it comes to milling teeth, there's a billion different kinds of milling teeth. Okay? When we try to establish which is the best tool, we need to understand our typical applications. Hard asphalt, soft asphalt, low horsepower, high horsepower. There's all these variables you need to take into consideration. Because if we're milling soft asphalt, majority of the time, we're going to see a lot more body wear on the tool itself, less carbide wear. Hard asphalt, more carbide wear, less body wear. We have to understand, because obviously changing teeth, that's downtime. So if we are in a tight situation, when we're talking time frame with the paving train behind us, we need to understand, like, okay, with this milling tooth I'm getting so much production out of, I need to understand my timeline. When can I stop, go ahead and change teeth? We talk about what happens with that cutter tooth itself. Okay, it's a really abrasive material, asphalt is. In case you didn't know. It's really abrasive. So what happens is these tools generate heat, friction. This works against the lifespan of this tool. So if you think about per revolution of every time that tooth makes a hit, it will generate 1,000 degrees Celsius. That's 1,832 degrees Fahrenheit per contact. That is a lot of heat. So you think about that heat, plus add the abrasiveness, what happens is that's where the tooth actually starts to break down. That's the carbide tip. With that, a massive amount of heat And that abrasiveness, that's where the particles start to wear the carbide. That's where the milling tooth wears. Okay, everybody got that so far?